Hello, my name is Antonio Fernandez, and today I'm going to present you my project, which is called Multimodal Sentiment Analysis based on video and audio inputs. This is a project that I did at IE University Robotics and AI Lab and the Cyber Physical Life Research Group with my supervisor, Susana Winat. Now we're going to start by establishing some context. The introduction of transformers in the AI landscape has led to huge improvements in finding solutions to complex tasks, which is why the main objective of this project is to find the balance between complexity and accuracy in order to get the best possible results for audio and video sentiment analysis. In terms of the datasets used to train our model, we first have the audio dataset CREMA-D. This dataset is composed of 7,442 voice clips with 91 possible voice actors. In terms of the speech content of these voice clips, we have 12 unique possible sentences and 6 unique emotions. These emotions are angry, happy, fear, sad, disgust, and neutral. In the video dataset, we have RAPDES. This dataset is composed of 7,356 video clips with 24 possible actors. In terms of the speech content of these video clips, we have 2 unique possible sentences with 8 unique emotions. These emotions englobe the first 6 emotions while also adding the emotions calm and surprise, although these emotions are dropped before training in order to maintain consistency between both datasets. Regarding the models that we fine-tuned for our framework, we first have our audio model, which is WAG2VEG2 large by Facebook. In order to train this model, we first have to standardize the length of the audios in our dataset, and we generated tensors to fit to the model. In the end, with 6 blocks of training, we managed to achieve a 72.59% accuracy on the test set. In the video model, we have Vivid B16x2 Kinetics 400 by Google. In order to train this model, we first have to resize the video in order to fit the parameters of the model, and we sampled 32 random frames to fit to the model. In the end, after 10 epochs of training, we managed to achieve 0.4 validation loss on our test set. Let's take a look at our final framework. We first start by feeding our video input file to a separation function. This function takes care of separating the video-only portion and the audio-only portions of the video and feeding them to our respective models. The video model takes the video-only portion and it samples the 32 frames, it processes them, and gives us an output the probabilities for each emotion inside the video. Similarly, the audio, it standardizes the audio length, it processes it, and it gives us an output the probabilities for each emotion inside the audio. Then, both of these probabilities are fed into a decision framework, in which we do some output weighting in order to give the final emotion output. Now let's take a look at an overview of the results of our training. As you can see here, we have 2 different architectures, one in which the models have similar accuracies and one in which the video model has a higher accuracy. When both models have similar accuracies, you can see that for 5 of our testing methods, all of them tend to show an improvement. However, when the video model is the one that has a higher accuracy, you can see that the only one that shows an improvement is the weighted average method. This method differentiates itself from the rest in the sense that it takes into account the accuracy of both models when giving a final output. That way, when it outputs the final emotion, it is more confident in its result. If you want to take a look at the code that I used to train these models, you can find the links to the Kaggle notebooks in the description, as well as the link to the full paper. Thank you very much for watching, and I hope you have a nice day.